4.3. Monotonic functions and the first derivative test. So we're going to kind of go back to basically that 4.1 kind of work that we did before. So 4.2 is kind of a jolt for some reason, but this is back to that 4.1 idea. So definitions. So increasing, decreasing functions. So let f be a function defined on an interval I and x1, whatever, and x1 and, let's see that, and x2 be any 2 points in this interval I. So 1. If f of x1 is less than f of x2, whenever x1 is less than x2, then f is said to be increasing on I. 2. If f of x1 is greater than x2, f of x2, when ever x1 is less than x2, then f is said to be decreasing on I. Okay, so, and the last thing is if a function is monotonic, which means let me state that over again. A function that is always increasing or always decreasing on I is said to be monotonic. So it's always going up or always going down. Graphically. So I'm going to show an increasing function and decreasing function. These are both going to be monotonic functions in my graph. So let's do just an always increasing function. So here's our increasing function. It just says some interval I. It doesn't say anything about a closed interval. What I know is I'm going to pick two values of x1 that are less than x2 always. So x1 is going to always come before x2 in this particular case. Notice how this function is increasing because it's going uphill. What that guarantees, notice how these are always, again, x1 is going to be less than x2. It's going to be the same over here. Notice since this function is increasing, the output of this one must be less than the output of this one. Now, these 2 points are not fixed here. Whenever this one is less than this one, its output of the first must be less than the output of the second. So if I plot it up to this point and then I plot it up to this point, I can see that f of x1 is definitely less than f of x2, and that's whenever x1 is less than x2. So if x1 is to the left and x2 is to the right, this is always going to be the case. So what I can see is that f of x1 is less than f of x2, so we are increasing. That means the bigger x values give you the bigger outputs. The bigger x values give you the bigger outputs because you're going uphill. Now, x1 and x2. So this one I'm going to do a decreasing function. notice that this is x1, this is f of x2, this is f of x1, and the next one is going to be f of x2. So what I notice here is, again, x1 is going to be less than x2 just by definition. Notice that if I have your x1 and your f of x2, that your bigger x values give you smaller outputs because it's going downhill. So this is decreasing. Now I consider this a monotonic function because it's always going uphill. I consider this a monotonic function as well because this is always going downhill. So both of those are pictures of monotonic functions. So this is going to be the, how can we tell if it's increasing or decreasing? And this is going to be kind of the shortcut to be able to do that. Now that we've defined increasing and decreasing, what is a way to check that? So they say corollary, but this is going to be the first derivative test for monotonic functions. So, suppose that f is continuous on a closed interval from A to B, and then you probably guessed it, differentiable, and differentiable on that open interval from A to B, because that's what everything seems to be. So remember, this is the beginning study of calculus. So what we've done is we're studying very, very nice functions. F is continuous on the closed interval and differentiable on the open interval. So that's why this is the case. It's very nice things. Not to say that we can't study other functions. What we do is we just kind of break them apart into these particular pieces where it actually has these. So it has these conditions. So if a function is discontinuous at a particular point, well, let me just look at the point to the left of the discontinuity, and then we look at everything to the right of the discontinuity. So we can still get around these. So if f prime of x is greater than 0 at each point x that's inside this interval from this open interval from A to B, so all the points inside A and B, then f is increasing on that closed interval. So if its derivative is positive for all those values, that means it's increasing. If the derivative is negative, though, is less than 0 at each point, x in that open interval AB, then f is decreasing on that closed interval. So, some graphs. So, do a couple monotonic functions. So let's say, let's just do, it's closed interval. So here we go. So closed interval. What we know for this particular function for this f on this closed interval from A to B, so this is from A to B. If I take the derivative here, the derivative will be positive for all values. So let me just pick, let me pick an x value. I choose this x value. It doesn't matter, any x value in between here. If I plot this up, remember what the derivative represents. The derivative represents the slope of this tangent line, right? And we notice that the slope of that tangent line, which is f prime of x, is definitely greater than 0 because the slope's positive. When it's running uphill, the slope is positive. We can tell that for all these points. If we can look at the slope here, positive, positive, positive slope, positive slope, positive slope, positive slope. So the slope of the tangent line for that entire curve is always positive because its derivative is positive. Now, if I have a function that's going downhill, I don't know, let's flip it over. See something like this. Now, A and B, so this will be our A and this will be our B. So what I notice is that if I pick any x value again, I don't know, let's try this x value. If I plot this up here, if you look at the derivative, remember the derivative represents the slope of this line right here, the slope of the tangent line. So I can tell you that f prime of that particular x value is going to be less than 0. It's going to be negative because the slope is negative. If you look at all the tangent lines, negative slope because it's running downhill, negative slope running downhill. All these slopes of tangent lines are going to be negative because this is running downhill. So what's nice about the derivative is we're noticing that the derivative gives you local mins and local maxes, but also the derivative can tell you if the function is increasing or decreasing. Because remember what the derivative is. The derivative is the rate of change. So if the rate of change is positive, then it's increasing. If the rate of change is negative, then it's decreasing. All right, so we're going to use the first derivative test. And see how we can use this. So example, determine the intervals on which the graph is increasing and decreasing. All right. So we're going to start with a nice graph. So let's say A. So f of x, so do a couple examples here, x cubed minus 12x minus 5. So I want to figure out when is this graph increasing, when is this graph decreasing, and so on. So in order to do that, what I'm going to do is I'm going to find its derivative. So here's kind of the goal here. What we're going to do is we're going to, on this x-axis, what I'm going to do is I'm going to find where the derivative is equal to 0. The derivative equal to 0 is going to give us our local extreme value. So it's either going to be a local minimum or it's going to be a local maximum. So let me give you just a scrap piece of paper. This is kind of the goal here. So say I have a function that looks like this. So what I know is I can find here's our x-axis. What I know is I can find the local mins and local maximums. And heck, it might, let's just say it goes on forever. It doesn't even need to stop. So this is just going to go on forever. So I know I can find the local mins and local maxes. Those are these points right here. So what I notice about that is, in this case, f prime of, let's call this C1, is going to be equal to 0. In this case, C2, also 0 derivative, f prime of C2 is equal to 0. So this C1 and C2 is essentially going to cut this x-axis into 3 intervals in this case. Now what you'll notice is inside these intervals, they are monotonic inside these particular intervals. What that means is over here it's either going to be increasing or decreasing. Here it's going to be increasing or decreasing. Here it's going to be increasing or decreasing. So inside these intervals, the only spot where it has the possibility of changing from positive to negative is at the zeros. The only way that the derivative is going to change from positive to negative is when the derivative is equal to 0. So what I can see is that over here, notice how it's decreasing. This is decreasing in here because it's going downhill. It's going to be increasing everywhere here, and then it's going to be decreasing everywhere here. What I'll notice is I'm going to pick an x value inside here, and I'm going to notice that f prime of that x value is going to be less than 0. I'm going to pick some x value in here, and I'm going to notice that f prime of that x value is going to be greater than 0. And I'm going to pick an x value in here, just any x value in this interval here, and I'm going to notice that its derivative is going to be negative. So negative derivative decreasing, positive derivative increasing, negative derivative decreasing. So that's kind of what we're going to do here. So back to our function. Okay, so what I want to do is I want to find the candidates where it's equal to 0 so I can cut my intervals into the slices it needs to be. So first I'm going to find, solution, I'm going to find my critical points. This is going to be the spots where the derivative is going to change from negative to positive because these are going to be the spots where the derivative is equal to 0. So f prime of x is equal to 0, or undefined. Those are still spots that could happen. Since this is a polynomial, this undefined is not going to be useful right now. So f prime of x is equal to 3x squared minus 12. So for our critical points, this is when 3x squared minus 12 is equal to 0, because it's f prime of x is equal to 0. F prime of x is equal to 0. So I'm going to solve this. So since this is a standard form quadratic, the quadratic formula, you can use the quadratic formula if you want to, but if it's easy, I'm just going to solve for it. So x is equal to plus or minus 2. So what I know here is we're going to have an x-axis here, and negative 2 and positive 2 is really what we're looking at. So I know that the function is going to be monotonic in these particular pieces. It's either always going to be increasing or decreasing here, increasing or decreasing here, increasing or decreasing here, because these are the only spots where it can change from positive to negative. So here's our intervals. The intervals we're going to look at is going to be minus infinity to negative 2. The other one's going to be minus 2 to 2, and the other one's going to be 2 to infinity. Those are my three intervals. So what I want to do is I want to grab a test point. I want a test point from each of these intervals. So a value in here. All I need is a point in this. So what I'm going to do is I'm going to pick a test point. Let's say I'll test this one. Let's test this one. So let's test negative 3. And I'm definitely if there's 0, I'm going to test the 0, and then I'll test 3 as well. Okay. So let's say negative 3, 0, and 3. You agree that negative 3 lives in this interval? Notice how 0 lives in this interval, and then 3 lives in this interval. So I'm just picking a test point just to see what they are. So x equals negative 3, x equals 0, and x is equal to 2. The reason why, again, is in this interval, it's only going to be increasing or decreasing, so the derivative is either going to be positive or negative for any point that I pick in there. So negative 3 is just, I don't know, it's the next integer below negative 2. You could pick negative 4, or negative 5, or negative 6, or negative 100 if you wanted to. Don't, but try to keep them small so they're easy. Again, I can pick any point here. No matter what point I pick, its derivative is either going to be positive or negative. So I'm choosing 0 because 0 is an easy number to work with. And then I'm picking 3 for the same reason I picked negative 3. It's the next integer above 2, so it's just easy. Okay, so remember, if I want to know if it's increasing or decreasing, it says that it has to go into the first derivative. So if the first derivative is positive, then it's going to be increasing. If the first derivative is negative, then it's going to be decreasing. So we're going to plug these values into the derivative. So what is f prime of negative 3? What is f prime of 0? What is f prime of positive 3? So plug them into the derivative, which is right here. So this is 3 times negative 3 squared minus 12. So 3 times 9 minus 12, so 27 minus 12. This is positive. I don't need to simplify it all the way to 15. 3 times 0 squared minus 12, plugging 0 into the derivative. So this is negative 12. And plugging 3 in, the derivative is a symmetric function. It's even. So I'm going to get 15 as well. But 3 times 3 squared minus 12, so this is also going to be 15. So since these derivative is positive, so this one's positive, this one's negative, and this one's positive, what I can tell you is that, so f prime of x, positive, negative, positive, right? So in this case, f prime of x is greater than 0, f prime of x is less than 0, f prime of x is greater than 0. So that means it's going to be increasing here. You can't see it. I'm sure you can see half of that. How far was it? That's great. So let me just go back to this. So the derivative for negative 3 is 15. The derivative for 0 is negative 12. The derivative for 3 is also 15. So that means 15 is positive. Negative 12 is negative. 15 is positive. So remember these are the values of the derivative. So that means the derivative is positive, so it's greater than 0 for this interval. For this interval, the derivative is negative, so it's less than 0. And then for this interval, the derivative is positive, so it's greater than 0. So when it's positive, it's increasing. When it's negative, it's decreasing. And when it's positive, it's increasing. So just to make sure, this interval is increasing, this interval is decreasing, this interval is increasing. First derivative test. For local extrema. Let me kind of show you what we're going to do here, just to kind of show. What I'm trying to get to is, this tells us something about the local extrema at these two values. So if it's increasing here, the graph is going to be going uphill, right? And in this interval, it's decreasing. So that means -2 is either going to be a maximum or a minimum. So if it's increasing here and decreasing after, that means at -2, it's got to be a maximum. Now at +2, notice this interval is decreasing and this interval is increasing. So at 2, it means it's going downhill as it gets to 2, and then it's going uphill as it gets after 2. So that means 2 would have to be, if it goes down first and up second, 2 would have to be a minimum. So the order of these increasing, decreasing, increasing, like increasing to decreasing, decreasing, increasing, means that this is a maximum and this is a minimum. So what I'm going to do is I'm just going to define that. So those intervals tell us something about those local maximums. So suppose that x equals c is a critical value, critical point value of a continuous function f, and that f is differentiable at every point in some interval containing c. So they mean the neighborhood. So they're talking about a local containing c. So that they just defined a local extreme value. Well, they didn't define it. They just said that they exist, except possibly at x equals c from left to right. So, number 1, if f prime changes from negative to positive, at x equals c, then f has a local minimum at c. Let me see. Yep. So it's negative before the derivative is negative, so it's running downhill, and then it's positive after. That's why I say from left to right. So negative before, positive after. That means it's got to be a minimum. 2, if f prime changes from positive to negative at x equals c, then f has a local maximum at x equals c. So what that means is if the derivative is positive first and then negative second, so it's going uphill first and then it's going downhill second at c, that means that has to define a maximum. And then number 3, we have to be careful because it doesn't always change. So if f prime does not change sign at x equals c, so that means it's either going to be positive on both sides or negative on both sides, then f has no extreme value at x equals c. So like our 2 pictures could be something like 3 pictures. Well, I keep putting vertical axes in here. Okay, so the first one, what we know is we have, let's see, it's going to look something like this. The second one will look something like this. The third one looks something like this. What we can tell is that this is going to be c, right? Its derivative is going to be equal to 0. Its derivative is going to be equal to 0. I know that this is a local maximum because f prime of c is going to be positive first, and then it's going to be negative second. So this is case 2. Case 2. And this one is case 1. And then finally this is case 3. So in this one, if it goes negative first, and the derivative is negative first, and then positive second, then this is a local minimum. And this one, notice how it didn't change sign. It was negative first, and it's negative after. That's considered a saddle point. So it is not. It's not an extreme value. So this would be a local max. This would be a local min, and this would be neither. This is not. So they call this a saddle point. When we get to Calc 3, you'll see why. You'll really see why it looks like a saddle point. But you can kind of sit on it. Is kind of the idea. All right, example. So A, what I want to do is I want to find all critical points. I'm going to actually tell you what. I'll do a part 2 in a second.